In class activity 15A, 1. You will be using graphs to examine the behavior of functions near x values not in their domain. Part A, graph the function g of x equals x squared minus 1 all over x plus 1 using technology. So let's go over here to the calculator and we'll go to the y equals screen, and I have this ready to go, and if we graph this, we see it looks like a line. So let's go back to where we were. And it also says, does this value agree with your graph? Well, if we were to graph g of -1, we get -1 squared minus 1 over -1 plus 1. And you see the problem here is the denominator equals 0, which we know we can't have. So for part B, it says graph the function f of x equals 1 over x using technology. So let's do the same thing here. And I'm going to go out of that, go back to y equals, switch graphs, and graph that. And there we go. That's what that graph looks like. Back in here. And let's see. We have f of 0 is equal to 1 over 0. And again, that denominator is the problem there. Can't divide by 0. So objectives for the activity. You will understand that rational functions have two very different types of behavior near points that are not in their domain. You will be able to describe and identify these different behaviors. Part 2. Boyle's law states that the pressure of a gas P is inversely proportional to the volume of the gas V. Suppose you put a little air in a balloon and seal it. What happens when you squeeze the balloon so that the volume of the gas is smaller? Well, we could think as the space the air occupies is smaller, the pressure in the balloon increases. If you squeeze the balloon too much, the pressure can increase so much that the balloon will pop. Part 3. Suppose that for a particular gas, P is equal to 6 over V, where P represents the pressure of the gas in atmospheres, and V represents the volume of the gas in liters. Part A, treating P as a function of V, what is the domain of the function? Well, does this domain make sense with what we know about the volume of the gases? So the V would have to be non-negative. So we could say the volume of a gas must be positive, and it cannot be equal to 0. Part B, complete the table for the given volumes. Notice that the volumes are getting smaller and smaller. And let me show you the table and keep that there. Hold on, there we go. Part 3 showing, okay. Notice that the volumes are getting smaller and smaller. That's the liters column. So if we want to calculate this, we'd have, well, 6 over V, 6 over 1, it's just going to be 6. Not really a lot going on there. And then if we have the 6 over, for the second one, it's going to be 6 over 0.1, and that's going to give us 60. And then 6 over 0.01, that will be 600. Part C, what happens to the pressure of the gas as the volume decreases? Well, the pressure of the gas would increase. Part D, could the pressure ever exceed 1,000 atmospheres? What about 20,000? Well, the value of P could exceed these values. That's provided the container holding the gas doesn't pop or explode. Let me just scroll this up here for part 4. Part 4 says, in an earlier activity, you worked with a scenario in which the height of a ball in meters was given by the equation h is equal to -4.9 t squared plus 20t. T is measured in seconds. The average rate of change of height gives us information about the velocity of the ball. Part A, it says find an expression for the average velocity of the ball from t is equal to 1 second to t is equal to 1 plus delta t seconds. You do not need to simplify your expression. Let's see how we could write this. Let's do this. We're going to write h of 1 plus delta t minus h of 1 all over delta t. So now we can write this as, using the equation, -4.9, 1 plus delta t, and that quantity squared, plus 20 times 1 plus delta t. And then we can write plus 4.9 times 1 squared minus 20 times 1. And this is all over delta t. Part B, what is the domain for the average velocity? Does this make sense in the context of our rate of change? Okay, so as long as the denominator is not 0, that's good. So we could say delta t is not allowed to be 0. Part C, complete the table for the given values of delta t. Notice that the values for delta t are getting closer and closer to 0. So if we were to complete the table, what we're going to do is we would write, let's see, let's write it here, 4.9, but negative 4.9. And then, well, 1 is just, it would be 1 plus, so delta t is 1 this time. We're going to square that, plus 20. 1 plus delta t is 1, so it's 2, plus 4.9 times 1 squared minus 20 times 1. And this is all over delta t, which is 1. So this ends up being negative 4.9 times 2 squared plus 20 times 2 plus 4.9 times 1 squared is still 4.9 minus 20 all over 1 is still going to be the same answer. So let's go ahead and go back to the calculator and all right, let's enter this in. We have negative 4.9 and then we have 1 plus 1 and that's going to be squared. And then we have a plus 20 times 1 plus 1 and plus 4.9 times 1 squared minus 20. And we get 5.3. So let's go back to our table here and put in 5.3. And let's do this again. Now this time I'm going to go to do the same thing. We have negative 4.9 and then 1 plus 0.1 is going to be 1.1 squared plus 20 times 1.1 and then we have plus 4.9 times 1.1. Nope, just times 1. Sorry about that. Let me erase that last one and put a parenthesis and then minus 20 times 1. And all of this is going to be over 1.1. So let's go ahead and enter this in. So we have this negative 4.9 times 1.1, and that's squared plus 20 times 1 9 minus 20. And when we divide by 0.1, we get 9.71. So let's go back to our table and we'll put 9.71 here. And that's a point there. And the remaining parts of this table, the value is going to be found the same way. So let's go ahead and put these in. I worked these out earlier. So that's going to be 10.151. And then the last number is 10.1951. Part D, let me just scroll up here. Part D, it says, what happens to the average velocity as delta t approaches 0? So the smaller delta t gets, or closer to 0 delta t gets, the velocity is staying around 10.2 miles per hour. So the velocity is staying about 10.2 miles per hour. Part E, for any values of delta t that are not in the domain, decide if they represent removable discontinuities or not. Well, that would be at delta t is equal to 0, there's a removable discontinuity. Part 5, what behavior did you observe in the graph near a non-removable discontinuity? Well, there, the graph seems to approach a vertical line that passes through the x value where the discontinuity occurs. And then part 6, what behavior did you observe in the graph near a removable discontinuity? Well, the discontinuity is not visible on the graph. The discontinuity is only visible from the table or knowing it's there. That's the end of this video. Thanks.